Hi, my name is Bailey Chambliss, and this is my Physics 2212 Lab Number 4, Magnetic Field of a Bar Magnet. So the purpose of this experiment was to measure the distance dependence of the magnetic field due to a small bar magnet, and compare your measurements to the distance dependence predicted by the equations on the on and off axis magnetic fields derived from the PHYS law. So using the glow script to create a computational model to determine the theoretical magnetic field, we will then compare the predicted and experimental values to determine the relationship between distance and the magnitude of the magnetic field. As the distance from the magnet increases, the magnetic field decreases. The magnetic field of a point on the parallel axis of the magnet is twice as strong as it is on the perpendicular axis. The experimental and the computational models differ. N equals negative 2.6758, K equals 8.382 e to the negative 7, and mu is equal to 3.8837. So our fundamental concepts and assumptions, modeling magnetic field versus distance, we have the absolute value of the magnetic field of the bar is equal to Ka times r to the n. The natural log of the magnitude of the x component of the B field is equal to natural log of K plus n times the natural log of little r. The on-axis B field formula is given below, and then the PHYS law is also given below. So our initial conditions are that the system is the phone and the magnetometer, and the surroundings are the bar magnet and the earth. This is our experimental design. These 5 steps are the ones that are given in our lab diagram, and then the pictures on the right are the corresponding images that they give us. So the second part of this was to record the value of the y component of the Earth's magnetic field in the appropriate location on the spreadsheet, which I'll show later. Mark the on-axis with tape on the phone being used for measurements and record data. Use the same experimental setup we used for the on-axis field, which was this. And find a distance d-perp where b net equals 100 mu naught times t, and record the value of the y component. Move the sensor distance d from the magnet and determine the x, y, and z components of the net magnetic field at this location, and then correct the previous y component and calculate magnitude of the b net, and then finally repeat 2 more times. 3 values of d and the magnitude of b net are found, and calculate the averages. So these were our results. Everything that I said in the last 2 slides was recorded into this Excel sheet. And our observations that were made were that the x component of the magnetic field increases as the magnetometer moves closer to the bar magnet. The x component equals about 0 when the magnetometer is a large distance away from the bar magnet. And then the calculations were that the absolute value, or the magnitude, of the magnetic field of the bar equals K times r to the n equals mu naught over 4 pi times 2 mu over r to the third, and we calculated that mu equals 3.8837. So this was the glow scripts code used for this experiment. It was given to us as a starter code, and then we just edited it with our information that we had. And then this is the results that it produced. Our observed results on off-axis B field is 4.1 e to the negative 5, negative 2.92 e to the negative 5, and negative 2.45 e to the negative 5. And that was a little different than our computational results. Our sources of errors could be inconsistencies in measurement, nearby electronics, or excess movement of the phone, all which are very possible. And then our discussion questions. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So if this was the case, the result would have varied in the x component. This would have then changed the n and k values due to the interface of the Earth's magnetic field. This would have led to an even greater difference in the experimental and computational values. And then finally, what if you were to stick 2 identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? If this were the case, we would expect the magnitude of the measurements would double without a change in the direction. This is due to superposition. In the end, the actual results would be the same, but with a difference in our magnitude. Thank you.